Hello, and welcome to this Let's Talk Machines webcast. Earlier this year, we submitted a survey to our users soliciting their feedback regarding their collective experiences using Pointwise. From this survey, we learned that some users regard importing and preparing their CAD models for meshing in Pointwise somewhat challenging, particularly when it comes to complex models or when dealing with what we often refer to as dirty CAD. Users were mostly unfamiliar with fault-tolerant or solid modeling meshing techniques in Pointwise. Many users indicated they primarily used either IGES or STEP, neutral CAD formats, for bringing geometry into Pointwise, though they also listed they were using third-party CAD tools such as CATIA, SolidWorks, or Creo. This was somewhat puzzling and may be indicative that some users aren't familiar with our native CAD reader in Pointwise. With the release of Pointwise version 18, a number of changes have been made to how Pointwise handles importing CAD files. Also, a few helpful tools have been added to assist users in quickly identifying potential problem areas with imported geometry. So in this webcast, we're going to demonstrate how you can leverage the latest tools available in Pointwise version 18 and provide you with a comprehensive guide for managing complex CAD models and preparing them to be meshed in Pointwise's latest release. To start, let's first define some terms used within Pointwise to help clarify how Pointwise handles CAD. Pointwise internally represents curves and surfaces as non-uniform rational B-splines, or NURBs. Additional information about the topology of these NURBs is also included using a technique called trimming. Trimming can be used to remove unwanted geometry from two surfaces that pierce one another via their intersection curves. In Pointwise, trimmed surfaces are wrapped in database entities called quilts. As their name suggests, quilts can be combined to make a composite quilt. Each quilt will be meshed using a single domain. Additionally, all of the quilts in a single body can be joined topologically to form a solid model where the seams between constituent quilts are closed for a given user-specified tolerance. Now, this last point is somewhat important and tends to be a source of confusion for many users. Therefore, it's worth repeating. The seams between adjacent quilts are considered closed for a given tolerance. Users often import their models into Pointwise and see discrepancies in their representation from what they look like in their CAD tool. The CAD tool used to create the model is using a built-in tolerance to define surfaces, their intersections, and so forth. Pointwise has a very precise geometry kernel. It has to be in order to resolve the very small spacing usually associated with boundary layer resolved grids, which are typically orders of magnitude smaller than the tolerance used by the CAD tool in creating the geometry. When a model is imported, the additional precision of Pointwise may expose flaws in the underlying CAD surfaces and their topological association, which don't appear in the CAD tool itself. As a first tip for users who create their own CAD and have control over how surfaces are created, consider that the model may be used for CFD or FEA simulations and decrease the tolerance used to define surfaces in your CAD tool accordingly before the model gets created and brought into Pointwise. This can really help you save time performing geometry cleanup prior to meshing. For those of you who receive their CAD from an external source, don't worry, we have more tips for you to come. So to illustrate the hierarchy of geometry in Pointwise, we begin with the underlying surface, which has topological information associated with it in the form of intersection curves, which yield the trimmed surface. In Pointwise, each trimmed surface is wrapped in its own quilt, and these quilts can be assembled into composite quilts, which will be meshed using a single domain. The quilts are joined topologically to form a solid model, where seams between constituent quilts are closed. Due to the differences in tolerances between the CAD tool used to create these surfaces and the tolerance in Pointwise used to interpret their definition, flaws can appear. Some of the most common flaws are gaps between adjacent surfaces or overlapping surfaces. The trim surfaces usually inherit the UV parameterization of the underlying surface, but then the trimming curves cause this UV parameterization to be invalid. Other times, the model includes additional surfaces other than the wetted surfaces needed for the CFD or FEA simulation. So a lot of time can be invested in identifying the wetted surfaces and removing the unwanted CAD. As mentioned earlier, after surveying users, we discovered that they may not be familiar with our native CAD reader, or what we meant when referring to it. Most are familiar with either IGES or STEP files. These are neutral CAD formats that have broad support amongst various computer-aided engineering tools. They are often used because of this extensive compatibility, though implementation of support for these neutral formats between CAE suppliers may be inconsistent and not conform to the latest format specification. This can lead to errors in how CAD is represented from one application to the next. These neutral CAD formats also don't always include all of the information about a model that the native CAD format supports. They're somewhat limited in that regard. For example, if you have named individual parts of an assembly or surfaces of a model, these names are usually lost in transition. Usually, the native CAD format includes the measure of length or assembly tolerance used when creating the model. And again, this information can sometimes be lost when writing out the model into one of these neutral formats. In addition to IGES, STEP, and other neutral CAD formats, Pointwise supports reading the native CAD part or CAD product files from CATIA, the part or assembly files in Creo, along with several others. Chances are good that Pointwise can read the native CAD files from the software used to generate the CAD model directly, and doing so is almost always preferable to using a neutral CAD format as an intermediate step due to the additional information about the model that is included. So this brings us to a recommended Pointwise meshing workflow for users to follow that should handle most of the cases they encounter. Import your geometry. Use the native CAD file format whenever possible. Pointwise version 18 has some new useful examine metrics that enable users to quickly identify potential problem areas in CAD after importing the model into Pointwise. Based on how extensive the geometry cleanup task may be after importing the geometry, and how often this model will be used for creating meshes, users should assess and determine which meshing approach, solid modeling or fault-tolerant meshing, to pursue. We'll delve into more details about both of these techniques shortly. Each approach has a set of strategies that we'll also cover. So let's begin with a demo and take a closer look at version 18's CAD import settings. From the File menu, I'll select Import, and from the submenu, choose Database. In the Open Save dialog window, I'll choose this Drive Air Smooth Underbody step file, which brings up the Import Database panel in Pointwise. The units frame is expanded automatically, and the option to read the units from file is selected by default. Units of measure in Pointwise often causes users some confusion, so let me take a minute to explain how units are handled when importing CAD. The Pointwise geometry kernel uses a scaling factor parameter and initializes this value to 1 for working in units of meters. If the units of measure for creating the CAD model can be determined from the file, then this scale factor is updated accordingly. If the CAD model was created in units of meters, and this can be determined from the CAD file, then the scale factor is unchanged. On the other hand, if the units cannot be determined from the file, then Pointwise forces this scaling factor parameter to remain 1, since any scaling would be meaningless. In this case, users are left to make a determination of what units the model was created in for themselves and apply a scaling transformation after importing the geometry. Now, if the units of measure can be determined on import, and a user has a preference to work in units other than those used in creating the model, then there is an option to apply scaling at import using the Convert To option and selecting the desired units of measure from the pull-down menu. Pointwise version 18 includes changes to how it determines the model size, and now should more intelligently derive an appropriate value from the extents contained within a CAD file. Additionally, expanding the model size frame now includes options for users to keep and use the current Pointwise setting, or explicitly set a model size using an available entry field. In the entity conversion frame, users can opt to have Pointwise split CAD surfaces at discontinuities, and options for doing this vary based upon the format of the CAD being imported. The Entity Visibility frame enables users to toggle the visibility of various database entities, and the Automatic Solid Model Assembly frame provides users the option to have Pointwise automatically promote free surfaces into quilts and assemble quilts into solid models using an assembly tolerance and quilt turning angle, respectively. This can save users familiar with how a particular model was created some time with solid model and quilt assembly. Lastly, the shell conversion frame provides options for importing unstructured wireframe data. In this example, I'll just continue with all of the settings in the Import Database panel set to their defaults and click OK to begin importing the Drive Air Smooth Underbody model. And here Pointwise has determined that the model was created in millimeters as displayed in the Messages window, but has encountered a problem with bringing in a surface. Clicking on the Show Details button expands the window and provides a list of surfaces that Pointwise is unable to import correctly. In this example, Underbody Smooth Trim Surf and Underbody Smooth Trim Surf 1 are causing issues. I'll go ahead and click Yes to continue importing the rest of the model, and once done, Pointwise provides me with some additional information about the model via a table in the Messages window. With Pointwise version 18, the problematic surfaces have been placed in groups, so I can quickly identify them and resolve any issues. Selecting a group from the List panel and using the Shift F2 keyboard shortcut to zoom to selection quickly highlights the problem in the display window for me. Here, I have an untrimmed surface. To fix this issue, I can select the surface and from the Edit menu, select Trim by Curves. This brings forward the Trim by Curves panel, and any curves that lie on this surface are highlighted in green in the display window. I'll select all of these curves and then click Imprint. The table at the top of the panel updates and shows the surface has been successfully trimmed. I'll save these changes by clicking OK. Now I can discard the unwanted portion of the geometry by selecting it and moving it to another layer or deleting it altogether. Now when I expand the List panel, it shows there are two solid models. One that was assembled using an assembly tolerance on import, and another for the trim surface I just created. Selecting them and choosing Assembly Tolerance under the Examine menu will show me what assembly tolerance Pointwise used at import in order to assemble the constituent quilts into a solid model based on the topology information that is provided in the CAD file. The legend shows that Pointwise had to increase its assembly tolerance to just over 0.1 millimeters in order for all of the seams between constituent quilts in the model to be considered closed or watertight. I know immediately from this information that my mesh size cannot be any smaller than this value, or I will run into problems with my mesh. Let's see what happens when I try to mesh something using a mesh spacing smaller than the assembly tolerance of the model. I'll pull up another instance of Pointwise and open a NACA 12 wing section I created. Here I have deliberately separated the upper surface of the wing from the lower surface using an offset of 0.01 inches. In Pointwise, I can assemble this into a single solid model so long as my assembly tolerance is at least 0.01 inches, and so I'll do that now. Pointwise assembles the two models into one, and notice that the curve along the leading edge, while appearing as two distinct curves, is shown as manifold. Let me give each quilt its own color to illustrate that Pointwise considers the seams between the quilts at the leading edge closed. Now let's quickly put an isotropic mesh along the surface using a mesh spacing larger than 0.01 inches. Pointwise doesn't have any difficulty doing this, but I'm really not resolving the wing's curvature, particularly near the leading edge. What happens if I redimension the connector along the leading edge using a grid spacing smaller than my assembly tolerance of 0.01 inches? I'll select the connector and then choose Dimension from the grid menu. This opens the Dimension panel, and I'll enter a value of 0.005 inches in the average delta S entry field. Clicking Dimension updates the number of grid points on the connector. After zooming in, you can see that the mesh along the leading edge is a mess. The vertices of triangles are being projected to the nearest underlying surface, but unfortunately, that surface is 0.01 inches away, and so the triangles become stretched along the lower quilt. The problem is aggravated further at the quilt boundaries along the root and tip of the wing section, and the mesh along the upper quilt along the leading edge is particularly interesting. Needless to say, the results of using a mesh spacing smaller than your model's assembly tolerance can lead to a number of undesirable, sometimes unpredictable problems with your surface mesh. Using other features like 2D T-Rex to resolve the leading and trailing edges with anisotropic triangles require even smaller grid spacing and will only make matters worse. Oftentimes, you encounter a situation where domains end up overlapping entirely, and you can't advance tetrahedra from such a surface mesh. So check the assembly tolerance of your models after importing them. Use this information to select an appropriate mesh spacing so as not to run into these sorts of issues. Pointwise version 18 also has another useful metric called boundary proximity. Using this metric can help users quickly identify gaps between adjacent models when Pointwise imports geometry that it was unable to assemble, usually due to missing topology information. If I import the same dry layer smooth underbody part as an IGES formatted CAD file instead of the step formatted geometry I imported earlier, then again there are some problematic surfaces that get collected into groups. Note, however, these are not the same as before. Selecting a group and zooming into the selection shows an invalid trimmed surface. The trimming curves used here have likely caused the UV parameterization inherited from the underlying surface to become invalid topologically. To fix this, I'll simply delete the surface, select the bounding curves, and from the Create menu, recreate the surface using a Coons patch. Once the Coons patch panel opens, I can simply click on the Generate Surfaces button to recreate the surface, and then click OK to save the surface. Now if I go back to the List panel, instead of 2 models as before, I have several. Selecting them all and using the boundary proximity metric under the Examine menu will calculate the distance between constituent solid model boundaries. Here the edges along the outer perimeter will usually show larger values since there are no models neighboring them. To get a better assessment of the spacing between model boundaries, I can adjust the maximum value of the metric to something more suitable, such as 1/10,000th of a millimeter. Doing so allows me to quickly identify areas in the geometry that are relatively worse off than others and which may have the potential to cause issues during model assembly. If I hover my cursor over these problem areas, then I can quickly gauge the magnitude of these gaps and use these values to assess whether I need to adjust the assembly tolerance from its default value. Once I have assessed how extensive the issues are with my imported geometry and how often I intend to reuse the geometry for creating meshes, then this information can help determine how to proceed with meshing the model. Pointwise provides two techniques or approaches to meshing. The first we refer to as fault-tolerant meshing. It foregoes geometry cleanup, and grid entities inherit any geometry defects. Users use the Grid Merge tool in Pointwise to identify and merge grid entities where needed. The second technique we refer to as solid modeling. Users assemble surfaces into a topologically watertight solid model prior to meshing. This process needs to be done only once, so in cases where a model will be reused to create more than one mesh, then this is usually the recommended approach. Even if the geometry won't be reused, but the geometry cleanup task doesn't look too extensive, then solid modeling is also recommended. To illustrate fault-tolerant meshing, I'll open another project I have saved which consists of a NASA reusable launch vehicle concept. Here I have isolated just a portion of the geometry, highlighting the vehicle's nose. You can see that each quilt has been given its own color, and no geometry cleanup has been done other than to isolate the surfaces for this launch vehicle's nose in their own layer. I'll quickly put a surface mesh on this visible part, and then select Merge from the Grid menu. This opens the Merge panel where I can see free connectors in red and manifold connectors in cyan. Free connectors are those used by only one domain. Manifold connectors are those that are being shared by two domains. Non-manifold connectors would be those connectors being shared by three or more domains. Were there any non-manifold connectors, they would appear in the display window colored in yellow. In the display window, I see that there are two places where connectors are being highlighted as free, but should be displayed as manifold. Pointwise's Grid Merge panel has a few options to heal the mesh at these locations. In the Auto Merge frame, users can provide a tolerance below which pairs of grid entities will be merged automatically. Node-node, connector-node, and connector-connector pairs that are within the given tolerance will be merged automatically. Proceed cautiously when using Auto Merge. It's a useful time-saving option for those familiar with their grids and requisite tolerances needed to merge certain grid entities. Options in the Merge by Picking frame let users explicitly select the pairs of entities they wish to merge. For example, I can hover my mouse cursor over one pair of the free connectors. My cursor changes to indicate that it is hovering over multiple grid entities, which I can toggle between using the spacebar. I can select one, and then select the other, click Apply, and the pair of grid entities will be merged. In the Merge Pairs of Entities frame, I can provide a tolerance in the available entry field and then toggle between the type of grid entities that I am interested in merging. In this case, I'm interested in merging pairs of connectors. After entering a suitable tolerance, the pairs of connectors are highlighted in the display window and appear in the table below where I can directly select them. Clicking Apply will merge the selected pair of entities, while clicking OK will merge the selected pair of entities and exit the Merge panel. And that's all there is to fault-tolerant meshing. You heal the faults in grid entities that were inherited by the geometry. Returning to the Drive Air Smooth underbody example, I have a number of models as shown in the list panel. In solid modeling, I work to assemble all of these models into a single solid model where the seams of constituent quilts are considered closed for a given assembly tolerance. To do so, I open the Assemble Models panel via the Assemble submenu found under the Create menu. If I begin by trying to assemble everything all at once, Pointwise is unable to do so. In order to determine what is preventing Pointwise from assembling everything all at once, I'll start by assembling models in parts. As I continue to assemble the model in pieces, I can narrow down where in the model I may have other issues. Eventually, I notice that a trim surface that looks like one that we fixed earlier may be the culprit. So at this point, I'll exit the Assemble Models panel, delete this surface, and recreate it using a Coons pouch. After doing so, and returning to the Assemble Models panel, I can finally assemble everything into a single watertight solid model. Once the model has been assembled, then I can begin assembling quilts. Recall that each quilt will be meshed with a single domain. By selecting all of the quilts in the model, giving them a unique color, and showing just the quilt's boundaries will provide some helpful visual feedback. Once all of the quilts have been assembled, then I can quickly create an initial isotropic surface mesh using the On Database Entities tool found under the Create menu. In closing, if you have control over how the surfaces in your CAD are created, adjust the built-in tolerance of your CAD tool to something more suitable for use with CFD or FEA mesh generation. This will save users a lot of time during, if not eliminate entirely, the geometry cleanup step. Use the native CAD reader in Pointwise whenever possible, so that Pointwise has all of the information about your geometry when importing it into Pointwise. In Pointwise version 18, there are a number of useful features that can help users quickly identify potential problems with geometry that has been imported. Pointwise includes a number of tools to repair flaws in geometry. Depending on how extensive this geometry cleanup task is, one can pursue either solid modeling or fault-tolerant meshing approaches to create a suitable surface mesh. In fault-tolerant meshing, users forego geometry cleanup altogether and repair the flaws in the grid entities directly using grid merge to obtain a watertight mesh representation of your geometry. In solid modeling, users clean up the geometry itself and assemble surfaces into a single watertight model where seams between constituent quilts are considered closed for a given assembly tolerance. This brings us to the end of this webcast. Thanks to everyone for joining us today. If you have any questions about this webcast, then please don't hesitate to post your questions to the YouTube comments section below, or send us your questions to us at letstalk@pointwise.com. You can also tweet your questions to Pointwise using the Let's Talk Meshings hashtag.